All right, good morning. How you guys doing? Tired? Hopefully a little bit rested? Maybe? Do you guys have a lot to do this, like today and yesterday? Gotcha. All right. Well, today's kind of our last class. I mean, obviously we've got Thursday as well, but today's the last class of covering new material. And so this will be kind of the remainder of what we need for the homework. You probably had about enough information, or if you took a look at the book, you probably could have got there for the homework anyway. But I wanted to finish that off. Might have a little extra time today, get out early. We left off here last time. I told you that essentially from that system where we had two BOD bottles, and we were thinking about the fact that if you add that seed water to a very dilute BOD bottle, we had to add a little bit of BOD because we have to add that stuff that the microbes like to eat, and that creates a little bit of a complication. And so then we have to calculate both the BOD in the mixture and the BOD of the dilution water itself separately, and combined we can find the BOD of the wastewater that we're actually interested in. And so based on that, just rewriting that up at the top here, we have that BOD times the volume of the mixture is equal to the BOD times the volume of the wastewater plus the BOD times the volume of the dilution water. Okay, so then there's some derivation that we can take a look at, rearrange some values, put all the volume components in terms of P, just a little bit of algebra involved there, using 1 minus P as part of that definition, and we can get this final equation here for BOD of the wastewater, simplifying. So I'm going to give you this on the equation sheet, which I will post your final one this week if I've not already done so. Okay. All right, so that's, I guess here again, just was going to reiterate that. You'll have the BOD of the mixture in one and the BOD of the dilution water in the other. So this one would have the volume dilution plus the volume of the wastewater, and this one's just going to be straight up dilution water. And in fact, that's probably misleading for me to call it the volume of dilution there. This would be just dilution only, just the dilution water. Because the volume here is going to be the 300 milliliters or whatever the bottle can hold. Okay, so that's kind of the approach. With that in mind, we can do an example problem here. We have a test bottle containing just seeded dilution water, and that has a DO level drop, so dissolved oxygen level dropped by 1.0 milligrams per liter in a 5-day test. A 300 milliliter bottle is filled with 15 milliliters of wastewater and the rest with seeded dilution water, so separately. And that's a 1 to 20 dilution. And that one experienced a drop of 7.2 milligrams per liter in the same period. So what would be the 5-day BOD value for the waste? So see if you can make sense of that. Take a couple minutes. Yeah.
What does B represent in the equation?
Good question, and I think I skipped by this too quickly before. So what does B represent? B is essentially the dissolved oxygen in the dilution water. So and the book just separates them because that way we're not confusing ourselves here with the DO.
What is the DO level drop by? It's kind of cut off.
By, oh, sorry, 1 milligram per liter. Okay, so we have two pieces of information essentially given to us as these drop values. So the DO drop, essentially that's referring to exactly what's inside of these values, right? These parentheses. The DO drop for the mixture, that's DOI minus DO final, that's the main experiment. So essentially we can say that our BOD in the wastewater is going to be that drop, 7.2 milligrams of oxygen per liter, minus the drop in the dilution water, which was a total of 1. So we don't even need to know the saturation value here because we're given the exact drop number. Now this is going to be that 1, but we're also going to multiply that by 1 minus P. And if P is 1 to 20 or 15 to 300, we should be able to, if we take 15 divided by 300, that should be the same as 1 and 20. Then 1 over 20 is 0.05, so 1 minus that is 0.95, so this will be 0.95. So essentially it's 7.2 minus 0.95 because 1 times that. And all of that divided by that 0.05. If we put this into a calculator, that should come out to be 125 milligrams oxygen per liter. Can leave the oxygen implied if we want. Milligrams BOD. All right, does that make sense? Okay, so I want to talk now about how do we track BOD downstream and kind of what happens when we discharge wastewater with significant BOD, and really how do we get to predicting that occurrence? Like what can we use based on the knowledge that we have to understand what's going on? So if we discharge BOD into a river or stream in particular, we can assume that's going to act kind of like a plug flow reactor, where there's a constant balance between re-aeration, so the equilibrium of our atmosphere with the water. If it's flowing quickly, there's more interaction with the air. If there's wind blowing, we kind of will just take that to be, rather than consider wind itself, we can consider how fast a stream is flowing and how sloped is its path. Because if you have a waterfall, that's going to act a lot different in terms of re-aeration than if you have a very gently flowing bayou. Okay, so that's going to be competing with the oxygen removal from biological processes. So we have this mass balance on oxygen within the water, and that's going to change based on how much BOD, so biodegradable stuff, is in the water remaining, and kind of how long it's been taken through the process. Okay, so we can look at that as a mass balance on BOD, and that's going to require the oxygen demand, and it's going to require the oxygen kind of re-aeration. So there's maybe a couple ways to look at it, and we're going to first focus on the BOD itself, and we're going to bring in a concept called oxygen deficit, so OD instead of dissolved oxygen, here in a moment. So I want to kind of paint a picture here of what this is going to look like for a stream or river where we have a saturation mark of what happens if we have fully saturated with oxygen. This is usually something like 8 to 10 milligrams per liter. That's O2 saturation. And then we can take a look at how the dissolved oxygen in the actual stream or river changes over time, or as a function of how far it's flown downstream. So that time and distance typically correlate pretty well, especially if we have a stream or river where we're not having inputs from other rivers and all that. Okay, so the dissolved oxygen then, typically in a realistic system, we will actually start a little bit with a natural deficit. There's a little bit of biological activity, a little bit of organic matter coming in from soil and stuff. So there's going to be a bit of oxygen deficit to begin with. And then as we discharge waste into the system, that's happening at time zero or at distance zero, then essentially the biological demand will begin. It keeps doing that. And it will begin flowing in such a, it'll begin decreasing in such a way where we have some curve that goes like that, and eventually we've consumed most of the oxygen demanding substances, and it will start coming back, traveling back upwards in terms of reducing the deficit. So we'll have some minimum, we can find the minimum value of the dissolved oxygen. That's going to be rather important in terms of how, if we can predict the minimum value, we can then assess whether or not that's going to be hazardous to the fish and wildlife. Is that going to cause a fish kill? Is that going to be disruptive to the ecosystem? Will it become really stinky? Or is it, we still have plenty of room there, and there's actually enough oxygen, it's just a little lower than it was, right? That's an important distinction there. The other thing is we can predict when that will happen or how far downstream that will happen. And so especially if we have multiple waste discharges in a system, we can then say, oh, well, here's a problem spot. Let's make sure that if there is some other wastewater discharge, it's not going to overlap and cause a big problem at this juncture because it's already kind of stressed to its limit based on the BOD that it's receiving. Okay, so then we can describe the oxygen deficit as the difference at any given point from the saturation point to, I'm going to try that again, the saturation point to the current mark. So this would be the oxygen deficit, OD, at some given time. Okay, so those are kind of the terms and the it's kind of the setup that we're going to take a look at in a couple of minutes. Another way we can predict in a manner what the BOD is without directly measuring it for 5 days is to take total organic carbon measurements. We talked about the chemical oxygen demand a little bit last time. This is a similar concept where we're just measuring how much total organic carbon is in the system. So so essentially it's a chemical method. We purge out all the inorganic carbon, so all the CO2, we acidify it and get rid of all that. Then you essentially give it really highly oxidizing conditions and let all the CO2 that it can escape, and you measure that CO2 and you get your carbon estimate that way for total organic carbon. And so we can use that. It's a quicker tool, and it can give us an indication of that food, the substrate. If we were to take a look at what's happening to total organic carbon, thinking about that last picture where we had the oxygen sag curve, where it sags down to a minimum and then starts coming back up. Well, that's happening in part because we're discharging TOC, so discharging organic matter, which is giving us the TOC. And essentially, that's going to be consumed by the organic, the biological processes, right? So that's going to be essentially decreasing over time. Typically in a natural system, there's going to be some level of organic matter regardless because of the soil, the sediment, all that. But if that was the only source, we could imagine it would eventually reach zero or very close. So that's happening over time, and that means that the rate at which oxygen is being demanded based on the waste material in the water is decreasing over time, right? If our TOC or our substrate is decreasing, then at some point the bacteria are slowing down because there's not as much food to eat, right? That's kind of the point I want to make with this graph, is that just by nature of there being less food in the water, that oxygen demand is slowing down and eventually stopping. Okay, so that means if we were to take, and what I'll do is I'm actually going to make this a 2-axis thing. So we'll say, so I'm just going to put these both on the same plot. I don't think I had anything else in mind. So we can call this total organic carbon milligrams per liter as that axis. And we said it looks something like this. And then we can have our dissolved oxygen. And let's say it's got a saturation mark. And it would look something like that. Okay, so at some point, our oxygen demand based on the amount of organics decreases, and we can watch that happen. Okay, so the question is then how quickly is the BOD removed, and how can we model that and then ultimately compare that to the amount of oxygen that's being added back? Okay, so we've defined BOD itself. We know how to measure it. There's a new term we're going to introduce that's essentially BOD remaining. Okay, so by modeling the amount that's remaining in the water, so BOD itself is a slightly counterintuitive term because it's how much oxygen will be demanded, or the amount of, this is the amount of oxygen that will be demanded relating to how much junk is in the water. So the BOD remaining is the remaining amount of junk that has not yet been demanded, has been consumed, providing oxygen demand. So it's not truly that complicated, but you can easily get it backwards in your mind. So I'm just warning you up front. So if we say L is the BOD remaining, then LT is the BOD remaining at some time. So if you took a sample and let the biodegradation process happen for 5 days, and then essentially what you have is your BOD remaining at time 5 is whatever your ultimate total amount of BOD that could ever be demanded if you left that bottle there for years and years, that value minus the BOD 5 value. Okay, so, and this is probably written somewhere, but essentially, if we define L naught as the total BOD that could ever be demanded, so that's our starting point. We start a BOD bottle, and the amount of oxygen that could be demanded from that sample, if you left it an infinitely long amount of time, nothing has been demanded yet. It's still full of oxygen, full of substrate. Nothing's been demanded from it yet. So we'll say nothing demanded yet or consumed. And we can say BOD or L naught is equal to BOD at infinity. Okay? Meaning if we left it there forever and measured how much was demanded, that's the value. Does that make sense? Okay, so the LT and L naught, two values here, and we can call this ultimate, that BOD infinite, we could say that's ultimate BOD, or L naught you could also call ultimate BOD. Okay, so then if we have that concept, we can say, well, how does the remaining BOD change over time? dLT dt. And that's going to be minus KLT. So we've got a first order decay reaction here where the remaining BOD is decreasing over time. Makes sense, right? And we can set that up as our typical mass balance for a batch reactor or a plug flow reactor. T then, of course, would be, if we're in a river or something, that would be our theta. But if you just think about it in a bottle, the amount remaining is going to be equal to the amount you started with times e to the minus some constant times the time it's been sitting there. That constant is going to be the BOD reaction rate constant, typically per day. So it's going to be per time units. Okay. Now, in practice, if we actually have a river, and we're discharging wastewater into that river, so let's say we have a river, it's flowing. Well, if we have a wastewater discharge, and we had a Q river flowing, say that wastewater is discharged in, then our L naught in practice is going to come from the combination of whatever BOD we had in the river, which sometimes there's a little bit, plus the BOD in that wastewater. Okay, so that then is our L naught is right there at that mixing point. Whatever BOD ultimate is there is what we define as our L naught. So that's going to be our representation of what's going on in terms of our starting point. So we need to account for what's in the river already, and we need to account for the flow in the river, mixing with our wastewater flow. So if that's our starting point, then we can model, okay, how much is remaining later, because the amount of BOD remaining, which is kind of analogous here to this total organic carbon line, that's going to drive the oxygen demand from the system, which was causing the dissolved oxygen to sag down to some minimum. Okay, is that making sense? Great. All right, so how do we put it all together then? And what do we do about reaeration? So essentially, we can describe that oxygen demand in terms of a deoxygenation rate constant. So KD here is going to be essentially accounting for that oxygen demand. That's going to be, if we take a look at this K here, this BOD reaction rate constant, it's going to be very closely related to this deoxygenation rate constant. And so this is a value that will typically we can find from a reference book or something. That's going to be somewhat specific to a river. You know, what's its temperature, what types of microbes happen to be in there, that type of thing that are describing that rate of oxygen demand. Now, we can have an overall rate of deoxygenation, RD, and that's going to be essentially this form here. So RD is equal to KD times L naught E times E to the minus KD T. So that's a description. The rate equation our book provides describing the rate of deoxygenation. It is a little confusing to me that the KD is appearing twice there. I'm going to trust that I took this from the book correctly, but I am going to double check that. But I've been using this for some time, and I think that's correct. I don't think you ever actually need that particular equation anyway, so let's not focus too much on that. I'll tell you if I got that wrong on Thursday. Okay, so essentially what my point is we can describe that rate of deoxygenation. It's going to be related to the amount of BOD that we started with, and of course how much time has gone by, and it's going to be at a first order decay reaction, because the amount of substance that we're working with is decreasing over time, and that's caught up in that L naught, which is actually might be why the KD is there twice. Okay, the reaeration. So how do we know how much oxygen is going back into the water? This is a physical process. This is Henry's law. It's an equilibrium process, physical, chemicals, kind of on the border of both. The gas is essentially, if the water is not at saturation, then gas will be flowing into it, will be exchanging with the water, and will be dissolving into the water based on that sort of that gradient, right? The water can hold more air, so as it's exposed to air, oxygen, in the air, then it's going to be crossing over. That process, however, is going to be driven essentially based on how much of a gap there is, how much of a deficit. So if there's a big oxygen deficit, then there's a lot of drive to push the oxygen into the water. And so the reaeration occurs faster when there's a bigger deficit. which is complicating but good, because if it's missing a lot of water, we want it to be replenishing fast. If the water is missing a lot of oxygen. Okay, so then this oxygen deficit, I think we may have labeled that as OD earlier, and I probably should have just described that as D, because the book does use D here, and I apologize, I'm just realizing that. So oxygen deficit is D. Okay, so then the reaeration rate is going to be a positive rate, and it's going to depend on that deficit. So it's going to be first order in relation to the deficit, which is, again, slightly backwards, because you can't define it by the amount of oxygen. You have to define it by the amount of oxygen subtracted from your saturation. Okay, so the definition, of course, is that for deficit is the dissolved oxygen at saturation minus dissolved oxygen at some time t. It's going to be, like I said, a first order rate constant here. Now the Kr is going to depend. I mentioned this last time and earlier, that the rate at which you're re-aerating depends on what's happening in your system. If you drive around Louisiana, you'll see lots of ponds, and in a lot of those ponds, you'll see fountains shooting water up into the air. Nice and pretty and all, but there's actually more than just the aesthetic factor that they have them. A large part is to keep them better oxygenated, so they don't get stagnant and stink and become a less desirable feature of the landscape, right? We keep them aerated pretty well, in part because there's just a lot of organic matter in all the soil here. All the sediment that's deposited over the years from the Mississippi that has created Louisiana, essentially. It's filled with lots of organic materials, lots of nutrients, and so there's going to be a lot of biological processes. And so if we want a nice pond that isn't overrun by plants, algae, bacteria, whatever the system happens to end up at, we don't want it to go anoxic on the bottoms, and we'll have methane and other anaerobic products bubbling up from the underneath, and probably be pretty stinky, swampy smelling. Well, we don't want that, so we do aeration, right? So that's one way to do that. And for natural rivers or streams, there is an empirical relationship that's been found to describe essentially that type of situation. What is the rate constant for reaeration given the speed of a river and the depth of a river? Okay, if you think of the Mississippi and how deep that is around where we are, it's upwards of 500 feet deep, right? It's very, very deep. It's flowing very, very fast. But the deeper it is, that's a lot of water that's not in contact with the air, right? So it's an interesting system, and this rate constant can give us some idea here. Empirically, researchers have found that if you take the speed to the 1/2 power, multiply that by 3.9, and then divide that by the depth to the 1.5 power, that gives you your Kr. Okay, so it's an empirical value. They tested lots of streams and rivers, measured their speed, measured their depth, and said, okay, well, there's some relationship, right? The faster it is, the more reaeration. The deeper it is, the less aeration. And so just by checking, 100 different streams or rivers, measuring these parameters, measuring the reaeration rate constant, with some experimental method, they came up with this relationship to say that value. Okay, so that's not derived from anything specific. That's just an empirical relationship there. Okay, so that'll be given to you, so we can use that if we have some information on a problem about the dimensions of a stream or river. Okay. I have a table here from our book. There's just a few examples of KR. So a small ponds and backwaters, it's 0.1 to 0.23 per day is the value, and that's at 20 degrees Celsius. And you can compare that to, let's say, a swift stream being about 0.7 to 1.2, 1.1, somewhere around there. And then rapids and waterfalls just somewhere above that. Okay, so just as a quick example of those empirical values. Okay, so we kind of looked at this already, but a little bit more detail here. So if we, I guess we looked at the dissolved oxygen sag curve down at the bottom. But if we were to line that up with the oxygenation rate, so that re-aeration rate, how quickly is oxygen being added to our system? It's not being added super fast early on because there's a lot of oxygen in the water already. So there's a small demand, small deficit, but there's not much of an oxygen deficit at time zero. But as we get closer and closer to the minimum, so the highest deficit here, that's going to correspond, of course, with the highest re-aeration rate. And so if we were to take a look at the oxygenation rate, that is highest right there at the same point of our minimum oxygen. If we take a look at our deoxygenation rate, essentially what we're doing is balancing the two to get our oxygen curve here. So the deoxygenation rate is in line with that, the removal of the biodegradable stuff, the TOC. And so that's decreasing over time and just continues decreasing until there's some new input of organic matter. So that's gonna, I don't think it has to intersect precisely on the graph here, but the point is that that's just going to be decreasing, whereas the oxygenation rate and the oxygen, actual dissolved oxygen, are going to reach a min and max there kind of at the same point. Okay, and we call this the critical point, so the XC here, or the time, critical time, that's going to be the critical one, because that's going to be the moment where it matters the most whether or not the fish are going to survive, right? Or whatever other metric you have regarding your oxygen content. And a lot of times, if you're doing a study in this manner, you'll have biologists who know the particular river or stream and know what it needs, and you'll have a kind of some added context to relate our engineering numbers here, relating it directly to that ecological context to make a decision or design. Okay, so let's take a look at the oxygen deficit itself. So D initial, so D naught is initial deficit. D at some later point is our deficit at some time. So if we map the deficit over time, dD dt, that's going to be essentially the deoxygenation rate minus the re-aeration rate. Okay, so the rate at which the deficit changes is that. So again, deficit is how far we are from saturation. So it's going to be, if we're increasing the deficit, that means we're further from saturation. So that's going to be more deoxygenation. And then if we're reducing our deficit back to zero, that's our re-aeration process. So it's, again, sort of a backwards look at it. But if we do this, we take that dD dt and put in these two rates that we described. So the deoxygenation rate here minus the reaeration rate here. And I don't know if we said this specifically enough earlier, but if we are to take a look at the rate of reaeration, yeah. Question?
The negative K, would that be KD? For the E?
You know, that's a good question. I think why I paused earlier is I think this one's correct. I think it's probably not supposed to be KD up here when I wrote it here. I think that's probably the K from our BOD rate constant. So I'm going to double check and clarify that. I'll correct the notes, and I will also let you know on Thursday about that. So I think this version is correct. Okay. And so the rate of reaeration, if we're to write it out as a rate, is KRD. Okay, so all right, we have this system then, and then now we need to integrate. Okay, and if you think about integrating that, you might get a headache. So let's just let the book do that for us and move on with our day. Okay, you all had kind of blank stares there for a moment. Okay, so turns out that if you do integrate that, D is this entire system here. Yeah, I need to check on this K here because it's now, we now have e to the minus KD. So maybe that's KD the whole time, and maybe that's just the same as the BOD rate. I will check on that. Okay. However, this was from the book, and you'll have this in your on your formula sheet. Essentially, that's a description of the deficit given some parameters, right? The KD that will be given, the KR will be, you can calculate. So this is essentially given. This is given or calculated. So if we were solving for D, then that's kind of what I'm talking about. The time would probably be given. Maybe you'll have a system where you need to solve for the time, and then you can, based on something else, and then you measure the deficit. And then, of course, you might have some initial deficit at the very beginning. I've mentioned that most streams have a small deficit, so that would probably be given as well. But this would be your system. And that's the solution for the deficit at some time. Okay, now one thing, if you take a close look at this equation, one thing that can happen is, what happens if your KR happens to be equal to KD? Then you're dividing by 0. Okay, so if the rate constants for removal and addition of your oxygen equals 0 when added, KR equals KD, you're dividing by 0. Then we have another equation, but this is only for that case. It's a simplification. It's a different relationship, and really is probably not as precise and is only valid during that condition, and that is D equals KD L naught T plus D naught times e to the minus KD T. Okay, so that gives us the deficit at some point. If we are analyzing our system about how much deficit it can handle, that's probably going to be very useful. We can also very easily correlate that, say, oh, well, if that's a deficit, that means our dissolved oxygen is X, right? If we started with 10 and our deficit is 5, then our dissolved oxygen is 5. But how do we find that time or distance where that happens, well, we can take the kind of a similar approach, but solve for the time. And distance is related to the time based on the speed, so we can kind of interchange between those two pretty easily. Assuming the river velocity is constant and all that. River, if the stream channel changes, but it changes kind of consistently, like it widens, but it gets more shallow when it does, the flow rate should remain the same. It'll be different if it goes out into a delta where it's very wide and it's just going to slow down and all that. Okay, at any rate, we assume that the river velocity is constant, then the distance is the speed times the time. Or time is the distance divided by the speed. Okay, so we have this value here. If we were to solve for the critical time, that's going to be equal to 1 over kr minus kd times the natural log of kr divided by kd times 1 minus that initial deficit times kr minus kd divided by kd times L naught. Okay, so big fancy equation. Again, this is just simply a solution for that critical time, and I'm actually not quite sure exactly how it's derived. I think it's coming from this, not that one, from this equation where d is at a max. So if we found the maximum value of d and then solve for the time, I think that's what gets us here. Okay, I will give you this equation as well on the formula sheet. So the real things to keep in mind first are the kind of the vocabulary. What is each of these components? Recognizing that some of these you can just expect to either be given, or maybe that would be your one unknown. Kr is something you solve for. D naught is going to be something that you can expect to find some context for regarding, maybe that's something that you know something about your wastewater, you know something about your river. When they meet and mix, then you probably then have to solve for your initial deficit. Maybe the wastewater treatment plant's been aerating like crazy, and so when they discharge their water, there's no deficit. Even though there's a lot of BOD, they were aerating. But the river has a small amount of deficit, so then you have to average the two, combine the two to get your initial deficit for your new river that's the combined streams. And then likewise, L naught, kind of the same case. You have some amount of BOD that could be demanded from river and the waste. You need to get that starting point. So these problems are mostly just using the formulas, recognizing that this particular formula is only when Kr equals Kd, and kind of recognizing the terms otherwise. Aside from that, before we got to all this, there was a bit here about that remaining BOD, this first order rate constant deal. I'm going to come back to revisit this to make sure this is whether or not that is KD is equivalent. And I'll update you in the slides here. But essentially this process is going to hold true and can be done separate from the downstream modeling thing. You could just be dealing with a system of wastewater in a bottle. How much is remaining? How do you track that? Right. This part of it is kind of leads to that remaining BOD analysis and deficit analysis, all that. But this is also something we can deal with just as a kind of simple experiment in a bottle case. Okay. I think that's it. That's all that I had for you. Okay, we do have a problem, an example problem. So let's work that. Okay, so there's a wastewater in, I think, that previous example that we did, 5.6. No, okay. So wastewater from some example problem is has a dissolved oxygen concentration of 2 milligrams per liter and a discharge rate of 1.1 cubic meters per second. The river that is receiving the waste has a DO equal to 8.3 milligrams per liter, a flow rate of 8.7 cubic meters per second, and a temperature of 20 degrees Celsius, assuming complete and instantaneous mixing. So that's kind of telling you, you can kind of assume already that you have to calculate something that's that initial starting point after these two streams meet, right? The two flows. Estimate the initial dissolved oxygen deficit of the mixture of wastewater and river water just downstream of the discharge point. Okay, so I've got a table here for the solubility of oxygen in water. So we'll use the 20 degrees Celsius. And it's referencing some other wastewater or some other example. I think that's irrelevant. Just use this value here for the solubility of water, of oxygen in water. Okay, so take a moment and see about solving that problem. Okay, so you can probably see how I set it up. Essentially, just we're doing two streams mixing, forming one. I drew it out as a big river. You could also just have a kind of what we've done before with a spot where they mix, two streams coming in, one going out, and we want to know what's going out there. And in that case, I would label that as our D initial for the river just downstream. And that's going to be for the Q of the mixture of the two flows, where the two flows are wastewater that had some deficit and the river which had some deficit. Okay, and then the deficit is defined by, again, the DO at saturation minus the DO that we had currently. So in the wastewater, it said we had 2 milligrams per liter of oxygen in the wastewater. And so 9.09 was our saturation value minus that 2.0. That's a 7.09 milligrams per liter there. For the river, it was at 8.3 milligrams per liter. So that corresponds to a deficit of 0.79. And so essentially then we just need to solve for that initial deficit, and that's going to be, so QR was 8.7 cubic meters per second times the river deficit was 0.79. We'll add to that the QW, which was 1.1 cubic meters per second times that deficit, 7.09. And all of that divided by the new total flow rate, which would be 8.7 plus 1.1, so 9.8 cubic meters per second. So if anybody has that handy, I have not added that yet. That should give us our answer, and it should be okay that on the top we have milligrams per liter times cubic meters per second. Cubic meters per second is going to cancel out and we'll be left with milligrams per liter, so it should be 1.5 milligrams per liter as our initial deficit. And if we check, our initial deficit in the river was not quite 1.5, and so that kind of makes some sense that as it mixes with this oxygen depleted waste, we get a greater deficit in the water. But it's not enormous because there's a lot more flow of the river than the waste. Okay, so that checks out. Does that make sense? Okay, so I think this is, got one more example problem. I think this is probably it. Yeah. All right. Okay. So, example 5.8, just below the point where a continuous discharge of pollution mixes with a river, the BOD is 10.9 milligrams per liter. The DO is 7.6 milligrams per liter. The river and waste mixture have a temperature of 20 degrees Celsius, a deoxygenation rate constant, KD, of 0.2 per day, an average flow speed of 0.3 meters per second, and a depth of 3 meters. Okay, and it's a continuation of the other problems. It just kind of gives all the stuff there. So part A, find the time and distance downstream at which the oxygen deficit is at a maximum. and then also find the minimum value of DO. Okay, so it's looking for that time critical, which is related to the critical distance, and it's looking for the deficit, so that the deficit at the critical point, I'll say C, or you could say deficit maximum, and then of course it would be the minimum DO value is going to be the DO saturation minus the deficit, right? That'll give us the value there. Okay, so this I think is maybe a little bit going to be a little bit time consuming to get all the equations rewritten here. What I'm going to say is happy to go back over this on Thursday if you need, but take a look at the book. It's all solved there as well. So I'd just encourage you to take a look there. Happy to answer any questions up front here about what this process would look like, but otherwise I think I'm just going to let you have this on your own, point it to you as a place to study, and leave it at that. Any questions, concerns? Okay. All right, so on Thursday, we'll go through the homework. I think I did not go through the prior exam with you guys yet either, right? So we'll probably take a quick look at that as well, in case there's any questions. All right. Well, good luck with all the stuff you've got, and that's it for today.